Hello everyone, my name is Roger Fari and I would like to welcome you to another video. This is the second video of the video series Deep Learning that I've started to create. And before watching the second video, it is very important for you to have watched the first video or know gradient descent in a very good depth. If you know gradient descent, or if you have watched my first video, so now you're ready to start with this second video. In this video, we're going to compare and understand the difference between what is a model and what is a solver in regard with deep learning. And we're going to do that with an example. All right, let's look at my Jupyter Notebook files that I've prepared a lot of good material. All right, let's get started. Okay, so before we get started, of course, this video is all about the difference between a model and a solver, right? So we want to understand that at a very deep level for deep learning. In our way to understanding and being able to answer that question, we are going to work with a sample data set. So we first are going to understand a toy data set, and then that toy data set is basically a classification problem. We're going to model a linear model to solve this classification problem. So we're going to have only one model. But then after that, we're going to solve that one model. Find or train that one model by solving them by 4 different methods. And the last method is going to be gradient descent, right? So the gradient descent is the method that the deep learning uses. So we're going to compare our own code of deep learning with TensorFlow. So as I promised before, as we're starting this video series, we're going to be using TensorFlow. However, we are starting little by little. We're just going to get started with TensorFlow and understand what is TensorFlow and what is its most important contribution to deep learning, right? So that's all going to come in this video. And at the end, we're going to compare our own code and TensorFlow and see those contributions of TensorFlow. Of course, we're going to wrap up the video with a summary. All right, so of course, we will first import our basic modules, NumPy, Pandas, and Matplotlib. And this is our toy data that we're going to be working with. This toy data has 2 independent variables and 1 dependent variables. Basically, we want to be able to predict what label is based on the value of x and y, right? Before we take a look at some visualization about this data set, this data set is simulated as the name suggests, and the code for you to find is also shared in the GitHub repository. So it is generate data random. It is in the same folder as the data that we are looking at, the Jupyter Notebook that we are looking at in this video, right? So if you're interested about how I made this, just simulated this data, you can take a look at that file. But anyway, let's take a look at the scatter plot. In the scatter plot, we do see that we're going to have 2 sort of clusters of data objects, and lo and behold, the clusters on the bottom is one class, and cluster on the top is another class. So we've got a positive and negative class. Positive is when label is 1, and negative is when the label is 0. Pay attention, this is a rather large data set. We've got 200,000 rows and 100,000 of positive, label 1, and 100,000 of negative, label 0, right? So it's kind of a large data, and what we want to do is to basically create a linear model, right? This is a classification problem, of course, right? Based on x and y, we want to be able to predict label. Now we want to train a linear model. We want to define a linear model that has the capability to do the task of classification, right? So the model that we have is this linear model. Basically, we are saying multiplying W1, weight 1, by X plus multiplying W2 by Y plus a B, which is known as bias in deep learning, is going to give us a label score. And if the label score is smaller than 0.5, we would predict 0, which is the negative case. And if the label score is larger than or equal to 0.5, we predict 1, which is the case of positive, right? So we model this classification problem into this linear model, right? Now the problem becomes, what are this W1, W2, and B in such way that this model is successful classifying these data objects, right? So we transformed our classification problem using this model into an optimization problem. The optimization problem here is, as I said, is what are W1, W2, and B that is going to help us to have the best classifier for these data objects, right? So that's our problem. This is now our problem. This is an optimization problem. Why is it optimization? We want to optimize the performance of the classifier that has specific W1, W2, and B. We want to find these three values in such a way that we're going to have the best classification model, right? So let's go ahead and create a function as our model. So this is that function. Basically, we've got W1, W2, and B, and we return that. So for instance, if our X is 4 and our Y is 0, then if these are our parameters, which is W1, 0.5, W2, negative 1.5, and B is 0.5, our model would say the label score is 2.5. So since the label score is 2.5, therefore our label is going to be 1, right? So that's basically how this model works, right? So before we continue moving on to look at our solutions, our solvers for this model, let's sort of like visualize our linear model. For us to be able to create a line as a representative or model, we have to sort of like find that line, and that line basically reside in where our score label score is 0.5. So that 0.5 is the separator. That's the separator between the positive and negative, right? So if I were to find the line that is equal to 0.5, that actually the representative line that I have of my model per each set of W1, W2, and B, right? So that's basically what it is. So if label score is 0.5, and then I have linear XY based on XY, right? Based on W1, W2, and B, I've got X and Y. So I can find a line, right? Y is equal to negative X multiplied by W1 over W2 plus 0.5 minus B W2, right? So from here, I can simply do some arithmetic, some math to get this line, right? So now I create a function using this math that I calculated, this formula that I calculated, that will give me the value of the line. Based on X, it gives me the value of Y. So I can actually draw this line, right? So if my X is such, whatever value it is, and then I've got my parameters, W1, W2, and B, then I can calculate the Y. So using this, I can go ahead and draw my line to represent that. So this is the line when my parameters are 0.5, negative 0.5, and 0.5, right? So these are the parameters, and that's my line, right? So this is that line if I've got those parameters, right? So one thing that I need to mention before moving forward is that if you pay attention to this code, I am only showing some part of the data, right? So I'm just sampling 5 thousandths of each of the positive or negative case. The reason is because I've got too many data as far as visually being able to see how good is this line, it's kind of like hard because there are too many data here. So I'm randomly sampling them. I'm just like showing some of them, so I can have a better visual experience to be able to see if this line is any good. Of course, this line is not good because it is not really separating between the positive and negative case. I mean, this is easy to say by just looking at it. Now, this is actually the foundation of our first method, right? So the first method, basically, what we're going to do, we're going to play with these W1, W2, and B, right? And look at the visuals such as like this to see which combination of W1, W2, and B leads us to a better separation, right? So that's basically the first method, right? So to empower ourselves to be able to do this visual method of try and error, we create a function, we call it test params, that basically draw this visual, right? Draw this visual per the parameters that we input, right? So let's go ahead and give it a try. For instance, when we do that with those parameters, this is what we get, right? However, the beauty of this function is that now I can set in whatever parameters I want and give this a try to see how this line would change. You can see by changing it to new set of parameters, I was able to improve this, right? So before moving forward, please go ahead and sort of like play with these three numbers to see how changing them is going to impact this line. For instance, instead of -1, let me put 1 here. I can see that, you know, the whole representation, the way this line is like representing itself changed, right? Actually, -1 was better. Let's just go back to -1 and maybe this time change this 1.5 into, let's say, to 2.5. Let's see what change that would make. And it made it worse. So let's go back to 1.5. That seemed to be better. And now let's change this -1.5 into, let's say, -3. Let's see what's that gonna do. It made it worse too, but it kind of like shifted upward, so we actually just kind of shifted downward. So for instance, we can, you know, put it to -0.5. That might actually improve our line. It kind of did, but still is not as good as it could be, right? So what we can do here is, instead of like, you know, just randomly sort of like trying these values, we can take, you know, use the tool that we have, which is programming, to create a nested loop to try different options, right? So we create some options for W1, some options for W2, or some options for B, right? Using this list comprehension. And we've got 9 options for each of these 3 parameters. And then using you know, nested loop here, using a nested loop. By the way, if you know thinking of nested loop, you actually have to have 3 fors. This is kind of the same, but it's kind of neater by using this iter tools from the iter tools module. Basically, I have a nested loop over these 3 iterators. This is just basically simpler writing, but it's kind of the same thing, right? So now I can have, you know, all of the combinations of these 3 iterators and sort of look at their values, right? Look at this visual for that set of parameters, right? So when I start looking at these values, you can see that each of these are one line and not necessarily a good one. And, you know, it's no surprise because we're kind of shooting in the dark. We're just like throwing some options there. And hopefully, by scrolling down, we may come across some that might be good. For instance, this looks decent, right? You know, better than the others. And you can like scroll down to see if there is one. For instance, actually this one is not too bad, right? This one is not too bad, right? So let's just, you know, actually go with this one. You know, to as a, you know, tentative solution. You know, it's not a perfect solution, but it's a tentative solution. let's just go with this one as the solution that we come up with try and error visually, right? So this is our solution that we found, and we can go ahead and sort of like cement it by, represent it one more time. This is actually still waiting for this loops to finish its working. As we've already found something that we want to work with, let me just stop this and come here and redraw my solution. And for instance, with this line, right, so it's kind of separating very nicely, but it could be a little bit tilted this way, of course. However, by just shooting in the dark, this is pretty nice by finding it this way. So for instance, when we've got x as 2 and y as 6, this should give us a value that is positive, and it is positive. 16 larger than 0.5, it is positive, right? You can give this a try. This is a fairly good model for classifying this data set, right? So that's our first method, which is try and error using a visual detection of if our line is separating between our classes. However, that's not a very efficient tool, automatable. It's not automatable. There is need for human participation to sort of like make that better. We need to find a metric that the value of that metric tells us how good this classification is, right? How good this line or this model is doing for the classification of this data set, right? And in deep learning, we call that a loss function, right? So here we create our loss function by comparing what we predict and the actual value of the label, right? So this is the prediction. So the prediction comes from the model, right? And we also encode that 0.5 rule, right? The 0.5 rule that we had in our model, right? We had encoded in this model, right? It just gives us that label score, this function. Now we want to also get the actual value, if it's 0 or 1, based on this rule that we have. If it's smaller than 0.5, it is 0, larger than or equal to 0.5, it is 1, right? So we also have coded that here, right? So we have coded that here. If it's larger than or equal to 0.5, it is 1. Otherwise, it's y predict. If it's smaller than 0.5, and the reason that we put the y predict is because we want to still give this, function a capability to sort of like distinguish between the closer data objects here. All right. So once we create this loss function, now when we have a prediction, right? So we use our model to predict for everything in our toy data, right? So this is the prediction for every 200,000 rows, right? So this is the model, the label score. And when we calculate the loss function, it gives us a value. So this is the loss function of this solution for our try and error, right? However, since we are using a tool of programming here, we've got, we are in Python, literally, we can try all of them and now get the value of the loss function and just use the one that reaches the best loss function value, right? So this is basically the iteration over all of these combination of parameters. And once we find a loss function that is better than the best that we've found so far, we save that and we make a report, right? So once we run this, we found about 25, 30 times a new best solution, and the one that we find is -551, right? So this is the best solution, and let's go ahead and give this a try. And we can see this line is sort of like even visually is doing better than the line that we had already found from the visual try and error. So this is the contribution of a loss function in a deep learning training, right? So that's what loss function is helping us with. right? So we found two solutions using two very simple solvers. So now by now you start seeing the difference between what is a solver and what is a model, right? And I am intentionally showing you solvers that are not very complex or not very adequate for this problem to show you that the solver could be anything, right? So the third solver that we have here is a meta-heuristic solver. It's a genetic algorithm. A genetic algorithm is good for the situations that we've got different types of decision variables, and we just don't have any other better methods to sort of find a solution in a fast way. We might resort into genetic algorithm, which is a meta-heuristic algorithm, right? So if you don't know what genetic algorithm is, just think of it as a solver. And I'm just showcasing that we could solve the same problem, the same problem here. It is that basically what are those parameters, what is W1, W2, and B that makes this model to reach its best performance by genetic algorithm, right? So for the genetic algorithm, because we are using this genetic algorithm module, this module just takes just one objective function, right? So that's the way this module works. We have to pack everything into just one function, and we've done that here. So based on the x, that is basically three variables. So three variables. We calculate our y predict, and then apply our 0.5 rule, and then grab the sort of like the actual label, and then report our performance metric of these variables, right? So this is the genetic algorithm, and of course we've got our boundaries. We basically want to just search between -10 to 10 for each of these three decision variables, W1, W2, and B. And these are some hyperparameters of the genetic algorithm. I'll go over them just in a minute, but let me just go ahead and click solve here, because let me actually run this. This is gonna take a while for this to run. So while it is going, running, let me talk a little bit about what is genetic algorithm. Just use this opportunity. So genetic algorithm is a meta-heuristic. It's evolution-based meta-heuristics. Basically, you've got a population of solutions, hundreds of them in this sample, that these solutions basically share with each other the gene. That's why it's called genetic algorithm. These genes are basically the solutions, which are these numbers, coded into chromosome-like structure. So they mutate, crossover, and by doing those things, they move towards finding the optimality. It's a very short introduction to genetic algorithm. And here I've got max iteration without improvement as 100. Even though my number of maximum iteration is 500, if there are 100 iterations without stopping, without improvement, this algorithm is going to run. So any second now, even though we haven't reached our max iteration, this might actually just stop and gives us the solution, right? So this is the way this genetic algorithm has been coded. I might in the future have a video specifically to talk about genetic algorithm. However, in this video, we are looking at genetic algorithm as just one possible solver for the training of this model, this linear model. All right, I guess this is best to sort of wait to see when this is going to finish solving. Alright, so the working of genetic algorithm, as I said, didn't go all the way to 100%. So somewhere along the line, we had 100 different iterations that we didn't have any improvement, so it stopped, right? So we can see that it took 3 minutes and 52 seconds for genetic algorithm to finish its solution, right? So now we do see that the value of our objective function is way smaller than the visual methods that we have, and we can go ahead and actually run and look at the line that and actually see that this is actually a much better line as far as visual. And also we can compare the loss function value, which is smaller than our trial error. However, pay attention that the genetic algorithm solved this very simple problem. It took it almost 4 minutes, right? So genetic algorithm, like I said, is great tool when you've got larger problem and you don't have any other better method to find a solution for your problem. However, as the community know, one of the best way to solve the deep learning models and this and also this simple model is using gradient descent. Like I said, if you haven't watched my previous video about gradient descent, what it is and how it works, please watch that video first before coming and continuing watching here. So here we create another loss function based on our gradient descent, right? So now this is the same loss function as the genetic one, with a small difference. And the difference is that we are not applying our 0.5 rule, right? So the 0.5 rule that we had here, we are not applying that. We are basically trying to just work with the label score, right? And there is a very compelling reason for that, actually, why we cannot use this function for gradient descent. And the reason is, actually, think about this for a second. Why? Because this is a very fundamental understanding. Why cannot we use that? Think about what is gradient descent and how it works. And the reason is because gradient descent work on the gradient, right? The slope. And if we don't have the slope to tell us the direction of improvement, we cannot optimize. And with doing things like this, right, it cuts off the smoothness of our function, right? It basically, at some point, your value just gets kicked into 1, right? Once your label score is 16, 20, 1.5, all of them become 1. And that smoothness is gone. And when the smoothness is gone, your function is not differentiable, right? So that's the term that is used in the literature. If your function or if your problem is not differentiable, it is not smooth, you cannot have a slope or gradient, then you cannot use gradient descent. That's why we cannot use that function. We have to have this function that is smooth, right? So this one is smooth, and because of that, we can use gradient descent. So this is our loss function, and we start with an initial solution with gradient descent, right? So this is our initial solution, and this loss function is this value, and by this, for every solution, we have to find the slope for that decision variable for the loss function. Pay attention here. We've got more than one decision variable here. We've got 3. So we actually do a loop over all of our decision variable, all of our parameters, W1, W2, and B in this situation. And we find the slope or the gradient per decision variables, per parameter, right? That's what this loop is for, right? So we find those, right? For instance, the gradients for W1 for the initial point, initial solution, is -0.6, W2 -0.36, and the B -0.8. What all of these are telling us is that we need to move the value of our W1, W2, and B upward, meaning we have to increase them. Do you remember when we want to minimize, we have to go against the direction of our gradient, right? So let's go ahead and also create our function update parameters. And basically in update parameters, we've got a learning rate. And after some experimentation, I learned that this learning rate 0.05 is a good learning rate for this problem. And basically I extract the slopes, which are the gradients, and move the parameters opposite direction of the gradients. That's what the negative sign is based on the learning rate. And right now, based on this, I know that by the initial solution of this, I have to move up to these values based on those learning rate, right? So our gradient descent solution becomes very simple. We basically do this 500 times. For instance, the number of iterations here 500 times. And for us to actually have a quick look at what happens when we move towards the direction of improvement, visually we are also using our test params function, which basically gives us the representation of that line, that solution from the line being in our data, right? So let's go ahead and click run, and amazingly we will see that our gradient descent quickly start improving itself, right? So it moves towards the direction of improvement. So it finds the direction of improvement based on that smoothness that we talked about, based on the slope, and it just simply moves towards it, right? The movement becomes slower, but certainly the movement is there. So if I move kind of quick, you can kind of see that the line starts moving towards sort of the curve itself to sort of have the best separation between these values, right? So if I go down, you can see it start, it has that trajectory. It's moving in that direction. And by, towards the end of these iterations, you can see actually this is a pretty nice looking line, right? And it still is running. All right, so it's completed, and you might think, and you might say, it kind of took as long as GA. So what's the improvement here? And the reason that it's taking too long here is because we are drawing this involved visualization on each one of these 500 iterations. So that's actually the most time-consuming piece of this code. So if we eliminate that, we can go ahead and actually time this time and see how long that is going to take. And this is not going to be, of course, going to be less than 30 seconds. So this is going to tell us how long it's going to take, and we would see that it's a huge improvement comparing to the genetic algorithm. And it took 16 seconds, and the solutions that we've got is, significantly better than the try and error visual. And we can also see the visual, and the visual seems to have done a great job in separating these values. So that was gradient descent, using gradient descent to find the W1, W2, and B for the linear model, right? Now, we are going to start learning about TensorFlow, right? So the gradient descent that we did, it was our own code. But one of the major contribution of TensorFlow is the help that it provides. It basically systematizes the calculations of the gradients in a very useful way, right? So let's learn that and see how much it helps us in being able to get the gradients. At the same time, if it's also helping us with some improvements in the performance of finding these gradients and solving our problems, right? So basically, we're going to do the same thing. We're going to just use gradient descent, but this time we're going to use TensorFlow, right? So we import TensorFlow, and one of the things that, just simple about TensorFlow is that Tensor is basically is an array, is a matrix, right? So whatever data structure that you have, basically Tensor is the data structure. And the reason that we call it Tensor, we just don't call it array, like NumPy array or a list is that tensors are designed to sort of like keep their flow can be monitored in such way that we can get the gradient of our calculations very simply. So that's why we use TensorFlow, right? So we have to define our variable, right? So we've got our initial variables, right? So this is our parameters for our gradient descent, right? We start with 0.01, like, you know, the gradient descent that we had, our own code. And in our model, we also have to use specific functions of the TensorFlow. And the reason is, again, we have to use this function because we need for the TensorFlow to observe our calculation so it can give us the gradients, right? So that's the reason that we need to sort of like kind of complicate the calculation, the simple calculations of our model, right? So this is kind of the same thing. I mean, this is the same model. Let me just scroll up. Our model is very simple, right? So we've got just one line of calculation. And that line of calculation has turned out to this 3-liner here. And the reason is that we have to use the specific functions of the TensorFlow, right? The multiply, right? So we are basically multiplying W1 with X, and then multiplying W2 with X with Y, and then summing up those with this add function, and then adding that to B. And the reason is, like I said, TensorFlow needs to sort of like, you know, we use these functions so TensorFlow can observe our calculation so it can give us the gradient easily. So once we calculate, you know, use our model, you know, it calculates the values for us, right? So it's simply like, you know, the other model. We also can calculate our loss function for gradient descent for TensorFlow, right? So this is very similar, but again, when we do the square, right, we, instead of just, you know, using star 2, we're using the TensorFlow function, TF square, and also when we calculate the mean, we use the reduced mean of TensorFlow. Again for the same reason, it needs to observe our calculations in a specific way so it can give us the gradients. Now, here's the magic with the gradient tape. Now we can do our calculations, and after our calculations is done, right, we can say this base for this value, what is the gradient for this parameter or this decision variable, right? And it simply calculates the gradients for us, right? So it simplifies the process of calculating the gradients, right? When we coded this, right, we had to be aware of what is the process, what is the calculation, have a function to extract the slope, right? However, here, regardless of what it is, we can just go about calculating what we need to calculate, right, the loss function, and use this gradient tape basically to tell us the gradient of whatever decision variables or whatever variables we want based on our objective function or based on whatever value we want, right? And it just gives us the gradients very quickly, right? So as we have the gradients, now it's so simple to update our parameters based on the gradients the way we did, right? So it's the same thing. But again, here we have to use a specific function for subtraction, right? So because, you know, the gradient, we want to move in the against the direction of the gradient, we use assign subtraction instead of assign add, and we use the same learning rate, and you know, we just move towards that direction, and we don't need to return anything because one of the things about gradient descent is that one of the things about TensorFlow is that when you create a variable, the variable is a global variable. Inside the function, it doesn't change itself, right? So you have to use a global variable with TensorFlow. So our variable is global, we don't need to return anything. Even though we are changing this in a function, it doesn't matter, it just keeps its own value. And we can do this for 500 times similarly. and it's going to find the same solution, very similar solution, because these gradients might be a little bit different. If you actually look at these gradient values, if you're interested, these one and the extracted slopes, they're actually very similar. We do see that our problem solutions are also very similar. We can also, draw it, and we can see in the drawings they are very similar, right? So that was gradient descent using TensorFlow. So what is the difference between gradient descent with our own code, which was the extracting slopes, and the TensorFlow tape? First and foremost, let's go ahead and compare them based on their performance, right? So with the performance, we have to see which one is faster, basically. All right, so it took our own code around 16 seconds to do 500 iterations and find the solution. And it took gradient descent with TensorFlow 13 seconds. So we do have some improvements here, right, as far as the performance. And we're reaching actually exactly the same solution. And another thing, so as far as the performance, it's showing some improvement. But the most important one is that, again, you don't need to worry about calculating the gradient. You can just go about doing your calculations based on your loss function or whatever objectives that you have, and then get the gradients based on whatever value you want. It's just a systematized way to calculate gradients, right? So that's basically your introduction to TensorFlow. TensorFlow is basically its most important contribution. There are a lot of contributions, don't get me wrong. It's one of its most important contributions is that systematized way of calculating gradients. Let's have a quick summary of this video. In this video, we talked about what's the difference between a model and a solver. We saw that in an example. Model is what we sort of create as a model capable of doing the problem that we have, and we use a solver to find the parameters of that model to fit the data, right? So that's the difference between a model and a solver. This is a very important distinction for deep learning. And then basically we modeled a classification problem using a linear model, and then after that we solved it with 4 different methods. Try and error with visually, try and error with a loss function, and then with genetic algorithm, and then we also solved with gradient descent, one time with our own code, and then with the TensorFlow. So this was our introduction to TensorFlow. We did see how TensorFlow is actually serving us as far as actually helping us with solving our model, solving for the parameters of our model. All right, actually,